Okay, so in this part of the second tutorial, we're going to be solving only one question, and this is based on equation of state. Remember, it is the topic that we discussed before we started this chapter. It is this topic, the one with this equation, right? And we are going to be solving it according to these steps that I told you. So let's have a look at the question. The question states, determine the pressure of nitrogen, so our gas is N2, at 160 Kelvin and specific volume of 0.00291 meter cube per kilogram, using part A, PV equals to mRT, that is our ideal gas equation, part B, using the van der Waal equation, and part C, using the tables. Right, so we have to find the pressure. So let us start solving part A. It's very simple. Uh, yeah, PV equals to mRT is our normal ideal gas equation. We've done this thousands of times. I'm pretty sure that we all know how to do it by now. So what we do is substitute values straight away. So P into a specific volume equals to, oh, I should probably mention why we can substitute specific volume right here. So if we have PV equals to mRT, and if we do P into V by M, that is we send M to the denominator equals to RT. And this is nothing but the definition of specific volume, which is why we can straight away write P into small v equals to RT. And Z is 1 here. If you're wondering if Z should come here, it should not, because we're assuming it to be ideal gas, right? So substitute values. R value for nitrogen from tables will come out to be this value. It will probably be given as 0.2968 or something, but we have to convert it to joule per kg. Always remember, joule per kg. And in the table, it is often given as kilojoule per kg. We don't want this, we want this, which is why I have straight away converted it and written. Upon solving, we get P equals to 16.319 megapascals. Right? This part was really simple. All you had to know was the R value and its unit, and how you can substitute specific volume. Alright, moving on to part B, the van der Waal equation. Now, in the previous lecture, we had seen how any equation of state has a general form, right? P equals to RT by V minus B minus A V square plus C into B into V plus DB square. Right? This is for any equation of state. So our step 1 was to identify what equation of state we are using. We are using what model you are using, right? We are using the van der Waal model here, because we have to use the van der Waal equation of state. Now, if we refer to this table, we can see that the value of C for van der Waal model is 0. So this term becomes 0. We can see the value of D for the van der Waal model is 0. So this term becomes 0. And now our equation has simplified to P equals to RT by V minus B minus A by V square, which was the van der Waal equation if you recall. But this time we have solved it using this table, because remember, any of these models can be asked, right? And we have to substitute the corresponding values of C and D, right? Our step 2 was find A naught and B naught, and thus find A and B. So if we see above, the value of A is given by A naught R square Tc square by Pc. Let's write it. A naught R square Tc square by Pc. And the value of B is given by B naught R Tc by Pc. And if we see this table again, we can see that the value of B naught for the van der Waal model is 1 by 8. So we will put 1 by 8 here. And the value of A naught is 27 by 64. Right. So now all we have to do is substitute R, TC and PC. TC and PC I think can be found from table A.2, and R value we have already found it to be this from the tables again. So upon substituting, let us just do that. 27 upon 64 into 296.8 square into 126.2 square divided by 3.39 into 10 to the power 6, because remember it has to be in pascals and this is probably given in megapascals, so we have converted it to pascals. Similarly, B will come out to be 1 by 8 value of B naught, value of A naught, into 296.8 into 126.2 divided by 3.39 into 10 to the power 6. Our A will come out to be 174.594. Units are not really important right now because we know that this equation is correct dimensionally, because obviously we have gotten it from the table, right? B equals to 1.3811 into 10 to the power minus 3. So now we have all of the values required to substitute in this equation. So let us do just that. So P equals to 296.8 into 160 upon 0.00291 minus 1.3811 into 10 to the power minus 3 minus 174.594 upon 0.00291 whole square. I think it is correct. Yes, it's fine. So our pressure will come out to be 10440.35982 kilopascals. And you can see that if we convert it to megapascal, it comes out to be 10.440 megapascals, which will obviously be more accurate than using our ideal gas equation, right? So that is how we use the equation of state to calculate for any gas. For example, if it was given as the let's see SOAV model, right? We would find C to be 1, we would find D to be 0. So this term would become only BV and this term would still go to 0. Then again, we would have calculated the values of A and B using the respective columns. We would have gone here, we would have gone here. And since there is an F term also over here, we would have gone here, and then as we are given nitrogen gas, we would have substituted the value of 0.039 from this table into this, found F, substituted back into this to get A naught, then substituted the value of A naught into this formula to get A, substituted the value of B naught into this formula to get B, put all of those values into this equation and solved it exactly as before to get the pressure. So that is the general method for solving. Now we can obviously do it using the nitrogen tables as well, corresponding graph and all. So our temperature is 160 Kelvin. Is that given? Yes, I think that was a given, right? 160 Kelvin. And our specific volume is 0.00291. So let us draw the TV graph to determine what state our nitrogen is in, right? So then we can refer the correct table. Right. So I think it will be beneficial to determine the values of Vf and Vg. So we can see where our gas lies. Let me just find the table here. Right. Okay, so these are our nitrogen, right? So if we see, we actually do not have the entry above 126.2 Kelvin. So in this case, what do we do? In the regular tables, we don't have temperatures above 126.2. So let us look at the superheated table. The special thing about the superheated tables is that in the very first row, it tells us the saturation. So these are the all of the Vg values, the Ug values, the Hg values, and so on. What this basically means is that the first row of the superheated table will give us all of the values at this point. So while we will not be able to determine what the Vf values is, we will be able to determine the Vg, Hg, Sg, Ug, because the very first row gives us the values at this point, right? So from the superheated table, we will try to find the pressure at which the specific volume is the one given and a temperature is 160 Kelvin. And if we see that, we are able to see at the 10,000 kilopascal mark and 160 Kelvin row, our specific volume is just as given, which means nitrogen must be at this state only. So from the superheated table, we are able to get pressure of 10,000 kilopascal. And in fact, this is very close to the one that we got using the van der Waal equation. So this just goes on to show van der Waal equation is quite accurate. So that is how we will use all of the tables and the equation to find what is going on with the gas, the equation of state to find what is going on with the gas. If you didn't understand the usage of superheated table, we'll be using it quite extensively in the following tutorials as well, so stick around for that. In the next tutorial, we'll be solving some miscellaneous questions related to gas behavior and Raynaud's fraction.